Welcome back to our engineering mechanics lectures, for which we're starting a new topic that we term force system resultants. Now that we have a solid understanding of forces in 2D and 3D spaces, it's time for us to move on to moments. And moments, as you will see today, actually always are directed and therefore need to be expressed as vectors. But as an introduction to the general topic, I want to talk about it as a scalar first. And before we move on with moments, you may have heard about the topic before, just in a different form. So this is what engineers call this, but you may have termed this before torque. And I will talk a little bit more about this in just a second. But before we do that, let's actually look at our other goals for today. So first, I want to introduce the general concept. That's why we're talking about it as scalars, and we're not worried so much about the direction today, so that we can understand how engineers think about these kind of force systems. And then I want to, of course, introduce a proper notation so that we can talk about the rotational directions. And you will see that you will need a very solid understanding of a 3D coordinate system, because again, they are actually directed. And ultimately, we want to, of course, calculate the moments out of the plane of that force system. So we want to calculate the force system resultants, which are usually out of plane for in-plane force systems. And that is why we get away with expressing them as scalars for now. Because if we have an in-plane force system, and for an in-plane force system, just think of an XY coordinate system in which you have a force that is acting at a certain distance. So I have X and Y. And of course, when we talk about the out-of-plane force system resultant, that means that for the in-plane force system, for the XY coordinate system, we have either out of plane or into plane. So this here would be minus Z, and this would be plus Z. And today we will only worry about in-plane systems, so X, Y. So we will ignore the third direction, because we will just assume that the force system resultant will be either positive or negative. And I will show you a trick that allows us to then state that as a scalar rather than a three-dimensional vector component. So let's get started and define a moment. As I mentioned, the moment is something that you heard before, and a moment is what engineers call this. Technically, engineers should call this a force system resultant, but in real life, if you go into an engineering office and you ask somebody to calculate a force system resultant, most people would probably look at you with a big question mark on their face. So what physicists call this, and what you have heard about this before, is called torque. And of course, you remember that torque is nothing else than force times a lever arm, so times a distance. Which means that we always look at force times distance in units. So force times distance. And the way we would probably say that is in Newton meters, for example, or pound foot. And I want to, of course, be a little bit more precise about this today and explain this further to you, because there's some particular things we need to consider for the force and some particular things we need to consider for the distance. And in engineering, you would always find this to be called M for moment, right? So moment. All right. So first of all, what is a moment really? So take the ruler in front of you, and I will draw one for you because you cannot see me doing this in front of me right now. So I'll take a ruler and I hold it in my hand, and here's my hand. And then I apply a force to it, let's say in this direction. So there's the force, let's call it F. And let's also add a distance to the mix, because we will need this distance from the force to the hand. That is called D, or you can call it the length of the ruler, doesn't really matter. And what you will find if you hold this ruler in your hand is two things. You don't just have to actually push against the force in the vertical direction. You know this from vertical equilibrium, right? So we need a force here called F, otherwise the system would fall down. You know this from all lectures that we discussed before. This force is going down in the y direction, and so to create equilibrium, you better push against it. But now think about this. If you see this picture from now on, this should not be enough for you if you have a force acting here and a force acting there, because what really happens is this force wants to rotate the entire system down. So the force is actually wanting to make this rotate in this direction. And what you have to do with your hand is actually rotate against that. So you have to rotate in this direction. And now we can already talk about the 2D system and the 3-dimensional rotation. So think of it as having a rotational axis right here. And that rotational axis now has an action of this force going clockwise in this case, right? So this is going clockwise, and you have to rotate back counterclockwise if you look at the system from this direction. And so if I now add a 2-dimensional coordinate system, I have an x-axis here and a y-axis here. And you may remember that we had something called the right-hand rule for 3D coordinate systems. Again, we're not talking about 3D. We have an in-plane force system. So the force and the distance are in the same plane, in the xy plane. But remember that if you rotate from positive x to positive y, you usually end up with the positive z direction. And vice versa, if you rotate from, let's say, positive y to positive x, you actually end up with the negative z direction. And that is why we can describe this acting moment here, which is the force times the distance, and the reaction moment also by clockwise or counterclockwise, where clockwise actually would be a negative rotation, right? So clockwise is a negative rotation if you think about this. So let's put that in words, and let's write that this here is m about point O, let's say, which is F times D. And that is the action moment. So this is the result of the force times the lever arm. And I say it again, this force and this lever arm about this point O here, let me highlight that point and let's call that O. So about that point O is actually acting clockwise. And therefore I can say that MO action, so the result of the force times its lever arm, is acting clockwise. Which of course later on we just write as CW. And clockwise is actually a negative moment. So clockwise would be negative. However, this M reaction here, to keep it in balance, is actually the force times its lever arm, but in the opposite direction. So M reaction in this case would have to be counterclockwise. Or CCW, which then is actually a positive moment. So now you understand why we can actually ignore the third direction, although it will always rotate about a certain point, and we can substitute clockwise for a negative moment, meaning pointing in the negative into the plane, or we can use counterclockwise to move out of the plane, which would be along the positive z-axis. So that is one important aspect and why we get away with scalar, although it's always a directed entity, right? So the moment always has a direction to it. But we will get away with it by identifying it as clockwise or counterclockwise. And that is an important aspect, the first aspect we need to understand. But there's a second aspect which I encourage you to try with the ruler in your hand. And that is what happens if you let go. So only if you resist, only if you provide this M reaction, if you actually push up here and maybe hold down here, then you can resist the force times the lever arm. And if you let go, this whole system will, of course, not just fall down, right? So the fall down is actually prevented by you pushing up here. So what you can do is actually put your hand underneath the ruler and stop the clamping that you use with your entire hand here and support it by just a finger here. And then when you push down here, what happens is it will actually stand still here at the origin of the coordinate system that I choose here, but it will rotate down, right? So that is an important concept to understand, and it actually speaks for the fact that a moment is only the tendency to rotate. So the force causes a tendency to rotate, and the moment is only created if this rotation is prevented. And that is very important. So let's write it down. So the moment due to a force, and in reality I should say force system resultant, or system, I guess, due to a force system, is the tendency and tendency is the important word here, of the force to rotate the system. So let me rephrase this, because again, this is at the heart of moments. So moments are only created if there's this tendency to rotate. And tendency means rotation is not happening. Let's write that down here maybe. So no rotation. So in other words, if rotation is allowed, the moment will disappear. And you can also test this. And for that, I'm gonna draw your door from the top. So any door will do. Go to your home and go to the front door. And what you will have is a hinge on one side. So let's say there's the hinge, and then here I have the wall. And on the other side, of course, I have a wall too. And there's also the doorknob, right? So let me draw that in here. So I have this, and then here I have the doorknob, which is connected to the wall here, and that's why you cannot go in. And now I encourage you to go ahead and actually push this door. Push it to the outside or the inside, it doesn't really matter. What will you do? You will actually bow the door in this direction, right? You will actually bend the door, and I have to say again, this is the door from the top, right? So hinge, doorknob, and you push from the inside to the outside. And you make this door bow. And of course, hopefully you're not strong enough to break the door so that the door can actually resist this. And as long as nobody pushes the doorknob, you actually have a tendency for the system to rotate. And therefore, you have a moment. However, as soon as somebody pushes down this doorknob and the door opens, the tendency disappears and you actually end up with true rotation. The door will actually open in this direction, and therefore the bow will go away and there will be no moment created anymore. So that is the concept of a moment, and it is important to understand that we talk about the tendency to rotate. So tendency to rotate the system is what a moment does. So in other words, we can say that the moment is resisted rotation. And that is a very important definition. And so for resisted rotation, you need to also understand that rotation always happens about a specific point. For example, once you open the door and you push down the doorknob here, you will actually end up rotating about this point, which effectively you're doing when you push here with the force as well, but you just don't see it, right? That's the tendency. But once you open the door, it actually rotates about that point. And what does that tell us? It tells us the same thing that we were told up here, that there's always a point of interest that is relevant for our moment analysis. So for example, if you move your hand to a different location on the ruler, then you would of course create a different moment because you changed the D. And so in summary, what we need to state about that is that a moment measures the tendency of a system to rotate about a specific point. So what we need is a point of interest. So when we ask you for calculating a moment, we always need to state about which point at this point in your educational career here, because we need to clarify about which point. And about this specific point is actually the important part here of the sentence. So let's highlight that. The about is important to understand, and then a specific point. And that defines the moment. We need one last thing to define here, and that is what happens if you visualize the moment, or if you want to visually indicate what moment you have. So let's say you have a random axis. Let's say in this direction, it doesn't really matter. This is an axis. Some people then indicate a moment like this. So this could be a rotation. And if you would look down on the red arrow, you would say that this turns counterclockwise. And that, of course, in 3D can be very confusing, because you could also look from the bottom. And that is why sometimes if you have an axis that is like this, so let me clarify, this is the axis. But it's better then to define the double arrow head. So this would be the moment. And so you can show moments visually in two ways, either with a rotation about an axis, and this can be misleading sometimes. So therefore it's better to actually use the double arrowhead. And what this means is it is rotating in this direction, right? So, or about this positive axis, let's say. This becomes more clear when we talk about 3D vectors. But again, here on this page, we are only talking about scalars. But I believe we now understand what force system resultants are and what torque is and what engineers call a moment. We also understand that it is dependent on the force times the lever arm, which then means that it is creating the tendency to rotate. And that further leads us to the conclusion that we need a specific point to rotate about. And that if the system is allowed to rotate, then the moment is disappearing. And that is the general concept we need to understand about force system resultants. Although in this lecture I will focus about the numerical problems in a 2D descriptional sense, that means that we only describe our moments clockwise and counterclockwise, I want to go ahead and define the proper 3D definition of moments, since we're talking about moments right now and we don't have to come back to this in our following lecture. So let's go ahead and, while it's so much fun, define 3D moments. And therefore I have these pictures here created and I'm gonna add something to them. So let's say I have, for example, here an x-axis, and then the wrench here is actually the y-axis. And therefore you can say that this f here is actually parallel to the x-axis, so that's fx, whereas d is parallel to the y-axis. So fx is parallel to x-axis, whereas dy is parallel to the y-axis. And together they create a tendency for rotation about point O. So these force and lever arm create a rotation about this point. And of course, you can already see here we're pushing in this direction, so we're trying to loosen the bolt actually. And now for the 3D description, right, we rotate from positive x to positive y. So if we rotate in that direction, then we actually end up with a positive z direction. So in this case, m about point O is equal to fx times dy. But now the important point that I want to point out to you, it's not enough to just say about point O. It's also important to state about which axis this rotation happens. And you already understand this from our previous discussion, that if I rotate from positive x to positive y, I'm moving in the positive z direction. So I better state here that it's actually MO about the z-axis. And that means that here on the top, we actually have to identify this as z-axis. Now let's take a look at the next picture, where I'm going to add this coordinate system again for us. So let me zoom in and add an x-axis, and then also add an y-axis, which is acting in this direction. And now I have a force that is actually parallel to the z direction, and I have a d that is still parallel in the y direction. Of course, nobody really sane in their mind would actually push on a wrench this way, right? So this here is parallel to the z-axis. Let me clarify this a little bit better by adding the z-axis that is going down here. That would be the negative z-axis. And so the fz and the dy are now in effect. But again, nobody would ever rotate a wrench like that unless you try to break something. But it is important for us to understand that there's still rotation created about this point. So now we have a force parallel to z-axis, and our dy is still a lever arm parallel to the y-axis. And together, these create a tendency to cause rotation about which axis now? That's the question, right? So let's look at that. So now I'm rotating this force here, Fz, to this point with lever arm dy. And what that really means is that I'm rotating from positive y to positive z, right? So imagine this. So I'm turning from positive y to positive z, and that means that I have actually rotation about the x-axis. So about the x-axis. And that means that up here I need to add my headline x-axis. And this is important to understand that now I have MO about the x-axis being equal to Fz times dy. And maybe you start to notice a commonality here if I zoom out again and would take a look at both of these pictures. So you see that I have x, y, z. X, y, z. So it always has to be three-dimensional because you rotate about the missing axis, if you will. And this is a rule you can pretty much remember and engrave in your brain, because it's something you need to understand when it comes to 3D moments. But the general rule is that you always need all three subscripts. Otherwise, you cannot create a moment. And that takes us to our last concept here on the bottom of the page. Let's take a look at that now. I will add the coordinate system again. So here is my x-axis. And I have a y-axis. And so that means that I have an Fy here. So F is actually parallel to y-axis. And let's look at our D. Our D would be somewhere here, which is acting from there to there. So this would be D, and it would also be in the y direction. So dy would also be parallel to y-axis. And therefore, you really have no tendency to rotate. And I can explain this in two ways. One is probably what everybody is thinking right now, which is the y and y. I don't have two subscripts that are different from each other so that I could create the third one, which would make sense in the context of this entire page that we just created here. So this is the mathematical reason, if you will. That definitely applies. Therefore, you don't have a tendency to rotate. But physically speaking, it's actually more important to think of this as the point of interest. So the problem here is actually that the force passes through the point of interest. So Fy is passing through this point. The line of action of Fy passes through the point of interest. Let's write that down. That is very important. So line of action of Fy passes through our point of interest. And therefore, no moment, right? No moment. Because you cannot create a tendency to rotate, or like you can also think of it that it could not rotate. It doesn't matter if it's a tendency or actually created rotation. If you put a needle here, think of it as pinning a needle here, and then you pull with a string on that needle, you will not rotate that string about that needle. You will actually just pull on it. And therefore, you create no moment. It cannot be created. In other words, we need to say here rotation about no axis, or about no direction. And later on, of course, you will not always talk about XYZ direction. It will actually be randomly oriented. It will not be as beautiful as it is here or here or here. It will be random in space. But if you understand this concept of the direction, you will be a big step ahead, because as you know from anything in vector decomposition, you can always break it down into X, Y, and Z components. And if you understand this concept here, then you understand how the components create different moments. But for now, let's take away that we always have two dimensions that create the third one, or the rotation about the third one. And more importantly, that if our line of action of a force passes through the point of interest, then we will not create a rotation. Let me follow that up with one last thing here on the bottom. If, for example, I were to weld something to my wrench here, let's say I weld an extension to it here, and of course you have to imagine that the hand is gone there, it's welded to the system here now, and now I'm gonna add the force Fy, but I make it attack here, so Fy, then I actually would have a distance to the point of interest. And that distance would actually be this line here, or better indicated by this here, which then would be called dx, because it's parallel to the x direction. And now this would create a moment about point O. Although I'm using Fy, right? I just shifted Fy here because I extended my wrench by this thing that I welded to it. And therefore, I made sure that Fy does not pass through the point of interest anymore. And so what you have to take away from this is that it's actually always the force times the lever arm. As long as you do have a true lever arm to it, you will always create a moment. There's one more thing that we need to talk about. I will do that on the next page, but I want you to think about it right now with me. And that is what part of the force actually creates that moment, right? It's not just any force times any distance. There's actually something very important to take away from all of this here. It's kind of hidden behind it, but it is the fact that it's the force times what's often called the perpendicular distance. So what people often write is that m is equal to F times d perpendicular. And that is something that we get to explore a little bit further on the upcoming page. So now, to look deeper into the fact that the moment is always equal to the force times its perpendicular distance, let's look at this beautiful picture here, where you can see the wrench again and the hand that pushes on it, but this time the hand is actually not pushing parallel to any axis. It's actually pushing at a random angle theta. So to clarify that, let's add our 3D coordinate system again. So I have my y-axis here and my x-axis is perpendicular to that. So here's x and here's y. And now I have a problem here because this force is not parallel to the x or the y or the z-axis, it's actually random in space. To clarify how I'm thinking of this here, let me just clarify that this is a force in the xy plane, right? So it's acting in the xy plane, and therefore it's not parallel or perpendicular to anything. In real life, you would never do this because you intuitively understand this formula already. So you would never waste some of your force component, as I will show you in a second. You understand that your lever arm has to be perpendicular to your force, or you might as well say that m, and by the way, it's about a point always, is equal to F perpendicular times d. So it doesn't really matter which one is perpendicular to one. Of course, it's the same. If the force is perpendicular to the lever arm, then the lever arm is also perpendicular to the force. But let's understand that here we do not have that scenario. So what can I do? And what do you usually do intuitively in real life? You actually would apply your force automatically perpendicular to the wrench. And so I can actually symbolize this here, and I can add the force components. So this blue force has two components. It has a perpendicular and a parallel component. So let's say I have a parallel component right here. And then that, of course, must be pushing in this direction. And I'm going to call this Fxy perpendicular to d, right, if you will. So this effectively means that we're looking at Fx, right? So we get that Fx component. And I, of course, also have a parallel component, which I can draw into two places. And I do that for you because you would probably think that it applies here, which then would be acting at this point, and this would be Fxy parallel, but I think it's better to draw it up here because it shows us that we actually have the right angle here, and then we can also call it Fy. And again, intuitively, you already know that this force component is really what causes the rotation about this point. So you would never waste this part here. But if you were to do so, what can you do to really calculate this or to really end up with the right numbers here? You would pretty much calculate Fx by stating that Fx is equal to Fxy times sine of theta, right? So because the theta is actually on the opposite, or maybe let me make that clear here, we have theta here as well. And therefore, you can use the sine function. For completeness reasons, although we don't need it today, fy would be actually equal to fxy times the cosine of theta. However, what can you do now? You can now calculate the moment of your force at a distance dy, right? Let's do that. So let's take the moment here and calculate the moment, in this case about the z-axis, which would be equal to fx times dy. But we just rewrote fx as what? fxy times the sine of theta times dy. And what we said is that this here, this component, is really f perpendicular. And therefore, you probably remember that you used this before and you calculated actually 3D moments in your physics class before. And the way that was done was you were giving a formula to calculate the moment with the double arrowhead. And this actually only gives you the magnitude. Remember, we're talking about scalars here today. But what you were given is r vector cross f vector. And now if you remember your formula properly, then you may remember that it was nothing else than r magnitude times f magnitude times sine theta. That is one formula you can use to solve cross product problems. And now the question is, why did this work? Of course, you know this already because you follow my logic here. It works because fx sine theta has created the perpendicular lever arm. And the perpendicular force, and the lever arm is just r. So what I have done here is turn this into f perpendicular. And that is the reason why your cross product formula actually works to calculate those moments in 3D. And we will use this in the future a lot. But for now, let's just state here that we have rotation due to the perpendicular component. This is very important that you understand that it's always due to the perpendicular component. And let's write a conclusion sentence here, or concluding sentence. So in conclusion, the lever arm must pass through the point of interest while the lever arm must be perpendicular to the acting force. Otherwise, you waste energy, if you will, or you waste some of your force components. So in conclusion, or as a result of that, if the force is not perpendicular, so if force is not perpendicular to the lever arm, either the force or the lever arm must be converted into the parallel and perpendicular component. And of course, to use the perpendicular component. You won't need the parallel component for this. So please understand those two concepts. That's what we are trying to show here with this nice picture here. And again, I, in this case, used the perpendicular component of the force, but I also could have kept the force in its original form and then just turned the lever arm into its perpendicular component. Just for completeness, let me zoom in on that one and show you how that would look like. So I could have, for example, found a point where I end up with a right angle here, and then I would call this R, and I could also find the force times that distance, but that distance R here, based on the geometry given in this picture, because I was given this angle here, would have been a waste of my time. So it was easier to talk about it with the force broken down. But it doesn't matter if you take the force or the lever arm. You can always turn that lever arm. All right. You can always turn both, I should say, into the perpendicular component. So that concludes that portion. Now let's talk about the multiple forces. And what you see here now is a two-dimensional coordinate system, x and y, with three forces that all rotate about a specific point. So you can already tell that F1 rotates from positive x to positive y. Therefore, it's turning counterclockwise. F2 turns from negative x to positive y, which makes it clockwise. And likewise, F3 turns from negative x to negative y, which makes it counterclockwise. And remember that counterclockwise is actually considered positive, right? And you can always remember this from your first quadrant. From x to y gives you positive z. So that is how you do that. But what we're trying to talk about here is that force systems can be summed up, right? As long as forces times lever arm act within the same plane, and about the same point, they can be summed up. So what does that mean? So an engineer would say the sum of the moments about point O is actually equal to, and let's take a look at these circles here first, or the semicircle, or the portion of the circle. So M1, M2, and M3. So the way I would write this is plus M1, right? Because it's counterclockwise, minus M2, because it's clockwise, and plus M3. And let's just say that moments are counterclockwise positive. That is something that we definitely need to highlight. So let's go ahead and do that. This is something you need to understand. This is because of the right-handed coordinate system, right? So due to right-handed coordinate system. So because of the right-handed coordinate system, we call moments positive if they are counterclockwise. And now I can complete my formula here on the bottom. I can also say that it's plus F1 times D1, which is the perpendicular distance, of course, right? Minus F2 times D2 plus F3 D3. And that is what this picture here tells you, because we are finding the moment about point O for all of these forces that all act in the two-dimensional plane. We can actually sum them up, and we can just do the mathematical sum for force times lever arm. So really what you will see later on is that the sum of the moments about a point O, and since we're talking about 2D, it will always be about the z-axis, is equal to the sum of F times D perpendicular. And of course, we define counterclockwise positive because that's mathematically correct. And now we highlight this because that is an important concept to understand, especially for your upcoming homework, where you actually have to sum up different moments. So that clarifies how we find the moment for multiple forces that rotate about the same reference point. And the key word here is the same reference point. And of course, they have to be in a planar system, which here I identified with xy. And therefore, our moment will always be automatically about the z-axis, and it will always automatically be counterclockwise positive. This is a definition you see over and over in this class, so you might as well remember and understand this right now, because you will see this a lot in this class later on in a different context, and it is my experience that students often struggle with that. But if you already get familiar with what we talked about here, it should be a walk in the park for you, and I believe we can now conclude this page because we have all the information that we need now to put it to an example and to apply our knowledge so that we can solve problems as we see them in the real world. Let's move on to our example problems. So here we can see our very first moment problem as we would encounter it in real life. It's a pipe structure with 3 forces attached to them. And we now have to find the moment acting at point O. Let's read the problem statement. Determine the moment or the force system resultant that is acting at location O, right here, due to the 3 forces acting at the pipe structure. 1, 2, 3 forces, 300 Newton, 500 Newton, and 600 Newton, acting at a specific distance. The distances are indicated here. And my experience in the classroom is that 50% of us can solve this right away with the knowledge we just created through the lecture, whereas the other 50% struggle with it. And there's no good or bad with being able to solve it at this point or not. But I personally believe that it's always good to challenge yourself and struggle with it a little bit before I will present the solution to you. So therefore, I encourage you to do the same thing that we would do in the classroom right now. Just go ahead and give it a try. And again, my experience is that students have an easy time with understanding how much moment this force here produces, but then these two become a little bit tricky. And I encourage you, because it's really like a 5-minute problem once you understand it. Don't get me wrong, it shouldn't be 5 minutes for you right now if you don't understand it. But ultimately, it's a 5-minute problem, and therefore I encourage you to just go ahead and give it a try. Pause the video and then come back for the solution to match it up. There's no harm in getting it wrong. In fact, you should get it wrong right now just so that we can develop the right solution together, and so you will get it right on the exams and the quizzes. So pause the video and I'll see you in just a second. All right, welcome back to the solution to this problem. Let's think about what we need to do. We need to find the moment at this point, and as we know from before, the moment about point O is equal to the sum of the forces times their perpendicular distances, right? So that's kind of our formula. And of course, we identified counterclockwise positive. Now let's look at this picture. So this force has a lever arm, which is often obvious to students with 1 meter. And so it would be 600 times 1. I will write that down in a second. But it becomes a little bit more complicated for this and this one. But just take a look at this formula and think about the perpendicular distance, and then a sketch goes a long way. I will now go ahead and calculate or draw in these distances. So for the first one, we already know that this distance would be, let's call it D1 perpendicular. And for the second one, it probably is also still easy because I have this distance here. And that would go in this direction. So this would be for the 500. So this would be D2, let's say, perpendicular. And for the third one, it's the 300, which now causes confusion often to students, right? But in reality, it's nothing different than the same thing. And if you struggle with it, just rotate your page by 90 degrees and understand that we're looking at this distance because that is the perpendicular distance from here to here. So I call that D3 perpendicular. And now I can go ahead and calculate that. And by the way, this is difficult to show now because I only have the screen here, but in the classroom I always tell my students, hey, when I need to understand if it's a positive or a negative moment, what I do is I pretend my left finger has a needle and I place the left finger, my left index finger right here, and I poke the needle into the piece of paper. And then I take my force, which in this case is pointing downwards, and I use my right hand or my pencil in my hand and pretty much align it with the force, and then rotate it on a string that I connect between the pen and the needle that I poked into the page, and then rotate it, of course, in the direction that the force is pointing. So what would that mean? That would mean that this force is rotating this way around. Let's do that for the second one. So this force here, if I put a needle here, and actually I have a line of action here, let me show you that as well, because I can really do that anywhere. So I have a line of action that really is in this direction. And so if I poke a needle here, then I have a string that connects the line of action and this one, and my line of action goes in that direction. So therefore it would rotate in this direction, right? Which would be counterclockwise. So that would be positive. Similarly, for the 300, I poke a needle here. I have a string that connects the line of action. So that would be here. And then I rotate in the direction of the force, which in this case would go down this way. So that would be clockwise. And you will see that now in my solution. So first of all, my M about O is equal to F1 times D1 perpendicular. Now that turns clockwise, therefore it's negative. All right, remember that moments are defined counterclockwise positive. And by the way, this is not part of the equation, so therefore I leave that out. All right, and then my F2, which is the 500, so F2, which rotates counterclockwise, therefore it's positive, times D2 perpendicular, and my F3 times D3 perpendicular, and that one rotates, and now I have to think about it myself, so it's rotating clockwise, therefore it's negative. All right, now let's put numbers to it. And I think at this point it's just mathematics, so that should become easy. So minus F1, which is 600 Newton, multiplied by the lever arm, which was 1 meter. Then we have plus F2, which was 500, right? 500 Newton. And now, of course, it depends on your geometric understanding, but ultimately what I have is 1 meter plus 2 meters plus 2.5 times the cosine of 45, right? 2.5 cosine 45. And of course, I understand that cosine and sine is really the same for 45-degree angles, but I want to make sure that we understand that we're talking about the component here on the bottom. And let me, for clarity, also add that, so that we understand that we're talking about this distance here, which is really 2.5 times the cosine of 45, and of course that's in meters, and so I shouldn't forget that here on the bottom either. But now I have that component complete, and I need my last component, which is the 300 newtons, and that was negative, so minus 300 newtons. And of course you already guessed what the lever arm is. It's times 2.5 meters multiplied by the sine of 45. So that is technically everything we need to come up with the final result here. But before we do that, let me zoom in and clarify where that distance is coming from. So I'm going to use my ruler and probably best show it here, because that's where the triangle starts. And I'll show you that this is 2.5 meters times sine of 45. Again, sine and cosine makes no difference, but this is the correct way of thinking about this, in my opinion. So now it's just a question of plug and chug, or actually like chugging, because we already plugged it. So what we will find is that our moment actually is positive 1,254 Newton meter. And there are two important things here to understand. Number one is that it's Newton meter. It's force times distance. That's how our units always are for moment calculations. And then also that we set plus here, because the plus tells us more than just it's a positive number. It also tells us that we're dealing with a counterclockwise moment. And that is part of my answer. I always have to identify that. So this entire line here is my answer, and therefore I provide the answer key. And you see that once you study these types of problems, they are fairly quick, right? It doesn't take a lot of time to do this. Of course, while you learn it, it takes some time to understand what is clockwise, what is counterclockwise, what is perpendicular, what is not perpendicular, and so on. But once you get there, this problem, which could be a nice problem on an exam or a quiz, should really not take you more than 5 minutes at maximum. But of course, right now you are in the learning stage, and therefore don't be hard on yourself if it takes you longer. In fact, let it take longer so that ultimately when it comes time to the test, you actually know how to do it under short time periods. But that concludes this problem, and we are now ready to move on to a little bit more complex problem. Here we go for our second problem about moments in planar systems or 2D systems. So what we have here is a cantilever beam that could be made from wood and has 3 forces attached. One that pushes down on it, one that pulls on it, and one that pulls or rotates it down. And so now we are asked to calculate the moment at A, so that's this point here, which is produced by these forces. So let's go ahead and do that, and let's memorize again that our moment is really equal to the sum of the forces times their perpendicular distances, right? So I now have to look at these forces and really break them down into their perpendicular components. That I believe is easier in this case. So I, of course, could take this force and extend its line of action. Let me show that to you. Graphically. So let's say I have a line of action here, and I could of course find its distance to the point of interest, which would be this one, and I'm going to call this R perpendicular, but that would be really difficult to do for all these forces. In this case, it's really easier to break the forces down into perpendicular and horizontal, perpendicular and parallel components, or vertical and horizontal components. So let's go ahead and actually turn the forces into perpendicular components. So let's get started with the 150 newtons here, and let's clarify that we have a force that's acting in this direction downwards, and that would be, let's call it F1 perpendicular, which that of course would be equal to what? 150 divided by 5 multiplied by 4. So that would be 30 times 4, which is 120 pounds. And of course, I could now go ahead and calculate the parallel component or the x component, right? So this here would be F1, let's call it x, or also parallel. And you do not need to calculate that because it actually passes, the line of action of this force passes through the point of interest. And therefore, we do not need that information. I'm going to skip that and move on right to the next force. And you can already see that the next force, 50 pounds, has the same effect. So the line of action passes through that point. I don't need to do anything with that. However, the force up here, I need to do something with that. So let's break those down, and let's understand that we have a vertical component, which is here. So let's call that F3, and we'll call that F3y because it's in the y-axis. And then we have also this component here, which is F3x. And F3x, for example, would be equal to 100 divided by 5 multiplied by 4. So that would be 100 divided by 5 is 20 times 4 is 80 pounds. And so then here we have 100 divided by 5, 20 times 3, if I'm not mistaken, is equal to 60 pounds. All right, and so now we have all our forces that we need. And last but not least, I need a rotational sense. So again, this is very difficult to show, and like if I had only have the screen here available. But let's imagine this once again, where I put a needle into my point of interest and then I connect a string to the force. So this force F1 actually rotates about that point clockwise. So that would be negative. This force here, F3, also turns clockwise. Therefore, that's negative as well. But then F3x actually has a line of action that goes in this direction. So it has a distance like that. If I poke my needle in here and have my rubber band or my string connected to that, I would find that it turns counterclockwise. Therefore, it's positive. Let's write that down. So let's write down M of A about the z-axis, of course, is equal to F1, which is 120 pounds, multiplied by 3 feet. That's that lever arm. And we said that's turning clockwise, therefore it's negative. Now I need to worry about the 60 pounds. So 60 pounds from F3 multiplied by 3 plus 3 feet. That's the lever arm. And that turns also clockwise, therefore it's also negative. But last but not least, I have the x component, which is 80 pounds. 80 pounds multiplied by, be careful now, 1 foot. And that turns counterclockwise, therefore it's positive. And so that 1 foot is this distance here really, because I have a line of action that goes here and then connects the perpendicular distance to A with 1 foot. And that is everything we need. So you see, it's once again just a single one-liner. And the result that we find for this one is minus 640 pounds. So minus 640 pound-foot. Pound-foot. And that is our result. And the minus tells us what? Exactly. It tells us that it's clockwise. So this is a clockwise moment, which is part of my answer. And I, of course, need to state my answer error. And that already solves this problem, which can be a quick solve, but can also be overwhelming if this concept of the right angled lever arm is not understood, or the right angled force, if you will. And once again, I didn't have to worry about the 50 pounds here and this component. I didn't even calculate it because it passes right through the point of interest. Be careful. Often students think that, hey, this is going in the negative direction, therefore it's a negative rotation, which you can see here is already not true. But this can be deceiving, because if this thing was built upside down, so let's say you have this force F3 acting down here with, let's say, 80 pounds. So if you have 80 pounds pushing to the left down here, then it would actually rotate clockwise, right? And therefore it then would become negative. Whereas if it's acting up here, it rotates counterclockwise, which is why it's positive here. So you see that this sign here, this and this sign has nothing to do with the direction the force is pointing into. So it's not like, so for example, here we have 120, and you could argue, hey, 120 is going down in the y direction. That's an argument I often hear in the classroom. But that is not related at all. The rotational sense is the only thing that matters. So it only matters what rotation you have about this point. And in this case, you have a force that isn't going negatively down, but it actually rotates clockwise, and therefore it's negative. And that is the reason why you see this negative. Not because the force is pointing downwards, but because the force is rotating clockwise. So this can be deceiving, as I said, right? So for example, if this force was going downwards on this side, then it would actually rotate counterclockwise, and therefore it would be positive. So it really has always something to do with the reference point and the point of interest. So please don't confuse direction with rotation. That's very different. But I believe that concludes this problem and tells us everything we need to take away from this. I hope this will help you on your homework and to get you ready for your exams and quizzes. We are now ready to move on to more complex examples. I will see you for those on the next page. So here we have our last lecture example, for which you once again have to find a moment about a specific point, which here is the anchor point A. So you see this is like a steel structure which has 3 forces attached to them, and you need to find the moment about that point. And rather than doing this numerically for you, you should do this on your own. I will now help you to understand these lever arms. So for example, for the first lever arm with the 20 kilonewton, right? 20 kilonewton, that one has a lever arm of, you guessed it, 8 meters, right? So that's the 8 meters lever arm. And that is the distance that is perpendicular from the point of interest to the force. So that's the 8 meters here. Let's look at the 15 kilonewton. The 15 kilonewton has a perpendicular distance of 1.5 meters. So the 15 kilonewton has a lever arm of 1.5 meters. And now we have the last force left there. I will break that down for you. I have a force that goes in this direction, which is 50 divided by 5 multiplied by 3. So that's effectively 30. And then I have also one that is going down, and that is equal to 40, therefore. So let's do the 30 first. So what is the 30 kilonewtons lever arm? That has a lever arm of 8 plus 2 plus 1. And that, of course, is also in meters. And that would mean that we're looking at this point here for 30, right? 30 has a line of action that is along this line here. And the perpendicular distance to that would be from here to here, which is 8 plus 2 plus 1. So we're looking at 11 meters here. And then last but not least, we have the 40 kilonewton. So 40 kilonewton has a lever arm of 1.5 plus 3. 1.5 plus 3 meters. And that is the distance from this force to this perpendicular lever arm, because you might as well have a line of action that goes all the way down here, which then would intersect with the x-axis. And so you have this perpendicular distance. So last but not least, you need to identify the rotational sense. That is the difficult one, I guess. The lever arms become easier and easier the more problems you solve. So let's look at the 20 here. If we rotate about this point, then we would rotate this way around, which would make that counterclockwise. So that would be, I believe, positive. So let's say rotation. And the first one would be counterclockwise, so positive. Now the 15 Newton is acting in which direction? It's acting downwards, so that rotates this way around, which makes it clockwise. Therefore, that is negative. The 30 is the next one. So the 30 would be this force here, which rotates this way around, which is clockwise. Therefore, that is also negative. And last but not least, the 40, which is rotating this way around, that's also negative. So you see the majority of the lever arms are negative here. And that will most likely end up with a negative moment as a result, which would then mean that this would be clockwise, right? So this would be clockwise, 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 and this here would be counterclockwise. So positive counterclockwise, negative clockwise. And I believe the numbers you can run yourself. This is all you need from me to help you solve this problem. I wish you good luck with that, and I definitely encourage you to really solve this, because I believe one of your homework problems is very similar to that. But we will talk about that next. All right, now that we studied moments, let's write down what our takeaways are and what we learned so far. Please indicate what is clear to you and what is not clear to you, and more specifically, how you think you can get a better understanding of that. That will really help you and help us to define how to train you better for the upcoming tasks. But once you've done that, let's take a look at the checkpoints actually of today's lecture so that we can agree on what we needed to learn here. First of all, we definitely understand the definition of a moment and that is the tendency to rotate. And the key word here is tendency, because if rotation is allowed, then it would create no moment. So we can check that off. We definitely understand that. Well, we also aware that moments are always generated by a force times its lever arm, and that both of these, the force and the lever arm, have to act in the same plane to generate a moment that is perpendicular to that force lever arm plane. And today you did not really have to worry about this. I mentioned this to you because we only dealt with XY planes, and therefore the moment was described by clockwise and counterclockwise, and therefore we got away with defining them as scalars and indicating the clockwise or counterclockwise. But in reality, those moments point in the z direction, and that's what we're talking about here, right? So you understand that the force lever arm plane is perpendicular to the actual resulted moment. All right, furthermore, we definitely understand that we need the perpendicular component, and this could be either the perpendicular lever arm or the perpendicular force component. It doesn't really matter, but only the perpendicular component really creates the torque or the moment. Please memorize this. And we also understand that the directional sense of the torque is really ultimately defined by the right-hand rule. I think we talked about this just right here when we talked about the force lever arm plane, because we only dealt with XY and it was always in the Z direction. So that's kind of repeated in here, but specifically for the right-hand rule. So I can check that off as well. Now, the moment, of course, always depends on the lever arm, and therefore it must be described by the reference point or relative to a reference point. Without a reference point, you would not be able to clearly describe or define a moment. And that is also reflected in the next point, where it says that you understand that no moment can be generated if the force passes through the reference point. Because in that sense, you actually have a distance of 0 to the reference point, and therefore the reference point is not really existent, or however you want to look at it. But if that is the case, if your force passes through the reference point, then you do not have a moment or a tendency to rotate, really, and therefore no moment. Furthermore, we understand that a moment system can be generated by multiple moments, and I can sum them up to determine the total resultant moment about a point. That is, of course, only the case if the lever arm and the forces act within the same plane. But for now, this is always the case here in this class because they are always acting in the XY plane. But you understand that if you have F1, F2, F3, and they all rotate about a point, then they can be summed up. So I can check that off as well. Last but not least, of course, we can calculate now, due to the examples that we did, the acting moment. And the key word here is really acting. So I encourage you to think about that. We have not talked about reaction moment yet. We only talked about the acting moment. And we can do that now for simple 2D structures with even multiple forces. That's what our examples were all about. So I can check that off as well. And that concludes our concluding lecture page here. And we are now ready to take a look at the homework. Let's get started on that. As always in our homework, we start from the very simplest case and move up in complexity. But for our very first problem, don't be surprised if it's too simple. There's only one force acting on this L structure here, or an L that lays on its side. And it's a cantilever which has a fixed point at O, and you need to find the moment that is acting at O due to this force. I don't think there's much that I need to explain to you here. Just make sure that you find the right lever arms, the right components, and you're good to go. Let's move on to the next problem, which is where the fun starts. So this looks a little bit more complex, or at least you have to do some geometry analysis here, because your force is acting down here on this steel structure and you need to find the moment acting at O. So I believe it is one force that requires one lever arm, but that one lever arm you of course have to find through geometry. Let's look at our next problem. See, now the structures become real and they start looking like what you would see in real engineering structures. So you have this system here where you have two forces acting on point A, and you need to find the moment at O right here. I don't think there's much I need to tell you. You see it becomes very much repetitive at this point, of course, with different outlooks on the actual problem. So for example, here we describe the forces differently just to get you used to that. And then this is a problem that we initiated in our examples. I believe you have everything you need to solve this properly. You find the moment about this point. So make sure that you break down the forces into proper force components, identify the proper distances, and then multiply it by the directional sense, or add the directional sense correctly, which means positive or negative. Positive for counterclockwise, negative for clockwise. Because it's so much fun, we have one more problem for you on the next page. Let me zoom out here first. So this is the first part of the homework, and we have this last problem here, which I believe is probably the most involved one in this homework set, but ultimately we kind of solved this as well in the lecture, so you should be able to solve this. You just need to find the proper force components and the proper distances to find the moment about point A. That concludes the lecture about moments as scalars. I believe I gave you all the tools that you need to solve your homework effectively, and I wish you good luck with that. I'll see you in the next lecture. Stay safe.